Do you guys have the mic too?
No, we don't have a mic.
You mind speaking in the gooseneck then? I know you're gonna have to go to the board to talk, right? But I mean, like, you don't have the mic, it's not gonna get very good audio. Unless you stay. Like it's.
Refresh. You didn't give access. I give audio access. What? Is that
Sorry, guys, hold on. This is not sharing. You guys hook up, with your laptop for the slides, or you have to do desktop, I don't know why it's not working. Laptop. Not showing on the server. Good, busy. Why it's not sharing the desktop? You can see like it should be sharing.
You made good progress in
I have mostly done. Unfortunately, I have been smaller for a few months. Like, rest of my classes.
Yeah, that's for sure. I'm taking a real semester, but I know where you click.
Can you share the laptop or like? Yeah, just, I don't know why that's not sharing over Zoom. Yeah. Okay, I'll take it. Sorry, I don't know why that's not sharing.
Yeah, I read a bunch of articles.
Oh, you guys have HDMI?
Yeah, it's game.
Did you guys have HDMI?
I actually did more of the written programming. So my programming efforts are already all like algorithms. I read a play yesterday. I have to do all that are left tonight. All about that. All of Matter Lab should be done in one sitting. Yeah, I miss a lot of ECP lectures, so I just feel different. Why that's not saying. Yeah, I'm missing the structure experience. Like, because I read so many right at this point. It's just been better next presentation semester mass. Yeah. Quizzes aren't that big of a deal. So did you name the class? Pretty serious. Video, carrier, regular quizzes. Regular, miss a couple. I mean, you miss a couple, you'll probably get it. That's fine. I don't suggest you guys too many though. I miss you. I think those are the it's not good. If you are catching quizzes, it's not gonna be. They probably count for 10% of those. So those PC classes will have to do quizzes, you know. A lot more. Like, are they in class quizzes? Yeah, they tend to be more for attendance, if anything. They're essentially like a couple EC classes do this. It's their version of having attendance. Oh, their quizzes are 5% of the all day. Yeah, that's what I thought. They usually count for things that are similar to attendance. Never mind. Yeah, you're not, it's not gonna be in the one for you. If there's one every lecture, that's 28, that is 2. That's like a fraction of a percent. Yeah. 290 is like that as well, where they have like the quizzes which are just, they literally say out loud, like this is basically just gonna be your attendance, because they're always. I think the reason, the big thing is actually ignoring, if you're just using materials really easy right now. Yeah. Like you're up to lecture 6 modules. That's a fun one. Yeah, because then I think, yeah, you have to, it's just like stuff that you should know more for be better at, but also have PGA. Yeah.
You know, just go ahead and just share. I'll just film the screen. So
It's not like
online, we're able to see the screen.
the materials just like. It's something that the board's attention.
No. I don't just think we've already on Zoom.
When I say like material, one specific.
Only problem.
Like current.
But it's not sharing.
I'm paying attention, I'm enjoying the material.
That's what should be out.
Yeah, and I have classes which are a lot of very specific hardware.
Yeah, I already started the recording, so.
Yeah, if you're not like,
That's.
if you don't have that,
I'll just film
like a slide that does around your head. Yeah, it's weird because I've been in freshman class and forever, like, yeah, these are what they're like. Like, it's just annoying busy work, but the material is so cool. But Adder Lab is so much fun. I haven't done Adder Lab, I just did an adder. So I made a 3-bit adder. I looked at Adder Lab, and I was like, oh shit, you how to do it. Mine uses up 2 breadboards, and it's like, it was mostly me just trying to develop everything on my own. No, it's not that hard, because most of the materials, but I kind of wanted to see how much I could optimize it. The thing about, so I was trying to build a book at adder. Let's take a look at adder, that's awesome. Or like, or forever trying to make my adder like login as opposed to and one like, well, then you'd like to.
I just go ahead.
See the projects. Have you found someone else to or it's just gonna be, we're gonna have to search for someone else. I think you should have at least one person who's actually. Because I've this kind of goes to me like it's like I have this stuff, so it's like taking the class, you're gonna do all the material.
Yeah, you can just move to the
I'm assuming everything. Yeah, if when it signups today. I've been, my head's been like elsewhere. I could email him and ask, basically ask and say, hey, I'm not enrolled in this class, but I would like to do a project.
Go ahead.
You see professors also, I say.
Alright, you guys are showing up on the.
On the slides, about the material.
Are you able to hear us on Zoom?
Or maybe I'll just.
Yeah, the slides are on Zoom, so you guys are good.
I skip this lecture. Would you mind a second? Yeah. Go to, let's go. It's just the project.
To you?
No, in general, I'm skipping like today's lecture. Oh, I mean, go to everybody's. I certainly don't mind. I mean, I think that if you're working with you.
Yeah, it's not, it's fine, it's fine.
I don't want you to be here like, all right, I don't know if I can trust each other to do this kind of work. I can trust you to do your part of work, especially because it's more of an open-ended thing, and you'll have to. I set up a regular thing on Thursdays, just talk about like the notes and stuff. Yeah, I think that would
No point.
I think that.
Hello,
I'm sure. So.
hello everyone. Sorry for the delay. There were some technical issues as always. So we'll be talking about the three projects that are up for grabs this semester. We have decided on three of them, and you will be choosing one of them depending on your group and what you like. So we'll be you're going through all these three projects in detail.
Sorry,
One is
excuse me.
currency exchange prediction. Next is autonomous
Uh,
vehicle driving, and the last one is blind source suppression on
Hello?
karaoke. So this is the first project. I'll just talk about this project.
Sorry, can the
So what,
TF
the
flag
goal
that
of this is
I'm not
project is
able
to
to hear
everyone
the audio
likes to earn
properly?
money. So let's
If the speaker can
predict how
actually
to
stand next to the
estimate the
mic, it'll
future
help.
currency depending on.
You guys please stand next to the mic.
Okay.
Probably like one person speaking at once.
Okay. So the motive of this project is to, depending on the previous values, you just predict the future values. For example, you may have USD, you may have some pounds, you may have INR, you may have different type of currencies. So you take the previous all predictions, previous all values, and try to predict the future. So these are the charts actually I just took from the Yahoo this morning. These are the charts that you will be using for the project. You will have all these values in CSV, which you will be downloading, and then you use this to predict the future graphs. This is just an example of the USD to Euro conversion and USD to CHF. So these are the outputs that was actually done last year by one of the teams. Here you can see that you can see the actual value, and you can see the predicted value of how we predict them. There are different ways you can do it. You have to think about the ways, and there are many things professor has taught over the last few weeks. You have to use some of them. So you may go online, look at other techniques that you may use, but your end goal is to determine the currency in the future. And the metrics here is MSE, mean squared error. So that is something you'll be using. You can look at the MSE, the value at the top. That is something that they predicted it with last year. So this is something you will be doing as the first project. The second project will be explained by Manoj.
So yeah, one of the interesting projects we have this time is autonomous driving. So you know that there are a lot of big players out there, when Waymo, Tesla, Cruise, and even Nvidia is starting their own autonomous driving vehicle. So this is such a big application, and people are making great strides in this. And by 2030, we are expected to have a fully autonomous vehicle. Under the hood, there are many advanced approaches. You might be knowing some reinforcement learning, computer vision, LiDAR-based 3D approaches. But most of these are all for processing sensory data. Whatever you see in the real time, the cars, the road scenario, processing this information is what this advanced technique is used for. But autonomous driving mainly is based on the case that you want to predict what's going to happen next and then take a decision out of it. So that lies the engine of this whole framework. And Kalman filter is one such good approach for modeling this next step decision making. So you'll be, I think it's almost 4 to 5 lectures away, you'll be learning about Kalman filter, how it's used to do a next state estimation, not just in terms of direct next step, but also you'll be considering noise and also uncertainty in your environment. So yeah, so this project highlights the use of Kalman filter for a simple simulation of autonomous driving. And you can see some of the graphs here, which we already tried out. So the top 2 graphs shows a simple simulation of MATLAB autonomous driving toolbox. The blue vehicle is our vehicle or ego vehicle, and all the red or some other boxes you see are some other vehicles that are there. So you need to figure out a way in the actual simulation to navigate and reach the goal, which is like this clustered set of points. So yeah, and there are also some failure scenarios where if there is a more complex environment, multiple obstacles at the same time, where this moving red car also appears to be at the same time of the blue car. There are some failure cases. So you're expected to explore different cases where this approach fails, and how the most recent research builds on top of this Kalman filter to avoid these failure scenarios. Okay. Yeah, next step. Okay, so I'll be discussing about the third project, which is blind source separation for karaoke music. So everyone here heard about the term karaoke, right? Yeah. So basically, it's one type of music entertainment system when you go for pubs or parties and a group of friends sing together for a music song. So here we're gonna implement the same kind of approach with machine learning techniques. So you take a few clustering algorithms like NMF and try to figure out how do you get your song out of it. Okay. So basically, I'll be showing you some sample plot. So I'll be showing you the sample plot of original audio, how it looks like, and the modified audio. And we'll also playing the song. It's the original song.
Sorry, folks on Zoom are not able
So
to hear your audio.
basically,
Can you?
in this, we only use NMF rather than the other clustering algorithms like ACA and
Can the
PCA.
presenters even hear us?
Okay.
Sorry.
So these are the three project scenarios which you have. And so for the first deadline, we have submission on October 24th. Okay. Now, if you guys have decided for which teammates you want, we are okay for that, and we'll be creating a Google form for that. And if you don't have other teammates as well, we'll be also creating a post on Piazza so that you can have other guys as well. That's it. And yesterday we have kept a post on Piazza that what are the timelines for the project duration, and also we shared the new IPS 2023 template that needs to be done on Overleaf. So these are all the things to be done in project. And yeah, and also if you have any questions about the project, I will be creating 3 tags like ABC, ABC. For the first project, if you have any queries, please make a separate post with me as a TA or whose project as a TA and an instructor as well. Let's say if you're taking blind source separation for karaoke system, tag me as well as the professor, not the other TAs. Okay, that's all from the project side, and he'll be connecting the lecture. That's exciting. And also for the forms, I'll be keeping the deadline on Monday as you have submission for homework 1 today, right? And also homework 2 will be released today, 6 or 7. How many late days can I use for this homework? For each homework, you can use a maximum of 2 late days, and total 5 late days are there for 4 credits. And those will be automatically be evaluated by Canvas. And also we kept submission rubric of homework 1, so you can see how many points you can get for each question, and you can get a good insight for that. Yeah.
Quick question on
Yeah.
more detailed instructions on projects.
Yeah, we'll make a good documentation of it, and we'll be posting it on Piazza.
Cool, thank you.
Any other questions? That's it. Okay, thanks.
All right. I will teaching today's class. So today's class is about detecting faces in image. And I'm Kashu. I'm a PhD student at LTI. And I was working with Piksha before during my visiting time. Okay, so today's topic. So previously, you've learned like how to describe a face. basically, using eigenface. So here's what we've seen so far. So like, we want to like do the detection of the face in the image. And the basic idea is like how we represent the face and like how can we like match the faceness in the image, given image, and detect that as a face. So oh, sorry. So okay, so basically we can use the like weighted sum of the features as a representation. So so let's say we have like weight W's and the feature vector E's. And we will use the weighted sum of those as a like approximate face to capture the like feature of the face. So we will have an image like this, like that. And we want to find the faces. And it kind of makes sense to like just simply match the pattern of the face with this given image. And but the problem is, how do you want to do that? How do we want to do that? One idea is to consider a typical face. So like the typical face like that one, and match with the faces within the image. Okay, so how we define a typical face and like what is a typical face? So given a like image like this, we apply some like typical face like that, and we want to like detect the face based on that. And so like what we are going to do is first convert the like given RGB image into a grayscale, because like the color is not very useful for like just detecting the faces. So we convert those into grayscale. And also like removing the color, it like helps the like skin shades also. And then, as I said, like the goal is to find like where in the image the like faces are. So basically we do the matching in the like sliding window manner like that. So we have like typical face and slide it to find a match within the image. And hopefully we can find some match like that to detect the faces. Okay, so how we like do the matching? So that's like simple way is to do the dot product between the like vectors. So like in order to do that, we need to first like express the typical face as a vector, and then we need to compute the like similarity between the like given image and the typical face. So the idea of like scanning the face to identify the match between the typical face and the underlying image is using something like the dot product. And this is, I guess, you all learned from the last class. Is that correct? Okay, yeah. And after doing some like like dot product calculation, you will get some like heat map like this. And whenever the like heat map peaks, you can expect that is the like kind of phase. And the problem here is we are kind of like getting some like red region here, but there's no phase over there. So okay. So in this like heat map, right on the top, the red region showing the area of like higher correlation between the given image and the typical phase. And because like the principal eigenphase is 100 by 100, you'll get like this reduced map. And it doesn't make sense to like calculate the correlation beyond that like border. And okay, sorry. And hopefully like we hope kind of like region with the face light up, but it's not like the best option. So like as I said, like this region is kind of like false alarms, and false alarm can have higher correlation than the like real face. This is the like issue with finding the maxima. So defining the match between the typical face and the underlying face, which was just about the product. So what happens if the like faces are not equally distributed like in this figure, but there are some like scales like this? We cannot just simply apply the like typical face over the image to like just simply scan as in the previous example. In this case, we have to like think about the like scales, because like it doesn't make sense to like scale the like typical face like that. So what we are going to do is to have some like scale pyramid like this and apply the typical face like that over the image of different scales. In this way, we can find the faces in different like scales with a similar matching strategy. And the new problem comes up when we're doing this. So like the problem is like the region we have to scan will like grow a lot. And this is gonna be a like problem in terms of computation. And especially like when we want to find a like small face in the large image. Also, there's another problem of like face like kind of tilting and not facing forward. And we can also like do the like similar stuff here by like kind of like shifting or like rotating the typical face and apply these over the image to find a like match. And this will also brings more like complexity to the like detection algorithm, right? And when you're thinking like applying those algorithms on the like camera or smartphone, that's gonna be problematic because the like computation resource is limited. And in such like in such kind of like limited environment, we want to like use some like lighter, faster method of like calculating or like detecting faces. And this like Viola Jane Jones method is the like boosted cascade classifier, which are going to discuss today. And okay, so I guess Viksha has the first poll here. So Mark, so okay, which one do you think is the true statement? Any idea? Two. Yes, that is correct. Okay. So coming back to the lecture, so faces can be like in many sizes, like as I said, and they can happen in anywhere in the image. And for each face size, and for each location, we want to like classify the like region, whether that region is face or not. And this is kind of like the binary classification problem, where we can deal with some like simple classifier. So the idea of AdaBoost is to create the like classifier based on the like combination of weak learners to come out with the strong one. So anyone know about the like definition of weak classifier or weak learner?
Simple learning algorithm that hopefully has a non-random chance of getting something right.
Yeah. So basically, weak classifier is something better than the random. And why we want to use the weak classifier is like if you consider having a strong classifier that has like 100% like classification rate on the training set, that means that is kind of like overfitting, right, to the training data. And there's no guarantee that can generalize to anything, like anything other than the training data. So the idea behind this is like you want to combine like multiple like weak learners and then like kind of like aggregate the decision of them to come up with the like better generalizable and like robust classifier. Does this make sense? Okay. Oh, wait. Okay. Okay, so here's the like algorithm overview of the AdaBoost. So does anyone know what will be the first step?
We utilize all of the weights for the training data.
Yeah. How about the second step?
To train one of your weak classifiers on the current like training data set plus weights, and then compute the error that that weak classifier had on that training set.
Yeah, that's correct. So So basically we want to find the like classifier that minimizes the error. So we want to increase the weight of misclassified instance and decrease the weight of the correctly classified one. And the idea is that if a very accurate classifier misses something, those are likely to be the hard instances, right? And you want to increase their weight for the next classifier to focus on them. And for easy ones, their weights are like reduced because they don't need much attention. And then the weight is like scaled. And if the classifier's like error is 0, what's the weight of misclassified instance?
The error is 0, then the weight of misclassified instance is negative infinity.
Yes, exactly. So it's infinity. So like perfect classifiers should have an infinite weight on the instance it misses. And if the error is 1, it's gonna be the opposite. So negative infinity. So and when the like error is 0.5, it is like equals to random guessing, right? And that's like not useful. So like weight should be 0. And and we use this like 1 minus epsilon over epsilon, where epsilon is the error rate, to kind of like set the scale. And similarly for the like weight of the classifier, if the classifier is perfect, weight is infinity. If it's random, weight is 0. And we get the like final classifier as the like weighted combination of weak classifiers. Is that okay? Okay. So here's some example. So I have a like table these like weights in the set of labels indicating +1 or -1 for face and known face. And threshold-based classifier is the like simplest form that can perform the classification. And we only need like 2 parameters to perform the classification. One is for the feature identity, so like what feature to look at, and the other one is for the like threshold value. And these 2 parameters can like completely define the classifier, and we use these because they allow us the very fast computation, since it's the threshold base. And this is important because it can work on like real time and on the edge devices. All right. So the like final classifier is the weighted sum of the individual classifiers like that. And if the sum is positive, it's a phase. And if the sum is like negative, it's not the phase. That's how like this final classifier determines whether the given region is phase or not. And now our job is to train a classifier of this kind and use it to scan the image window by window to find where the phase is. And training can take time because we need to like update those like weights over the like training set. But once it is trained and deployed, this is super fast. And here's a like example of showing simple like classifiers can like achieve very complex boundary. And all the like decision boundary are kind of like boundary edges are like horizontal, vertical on the right image, because this is a like property of my available features. All right. So we have poll 2. So for the first one, do you think this is true or false?
False.
False. Everyone false?
Yep.
Okay. Great. How about the second one? I hear some truths. True? Okay. Great. So why the first one is false? Which part is wrong? Okay. So training, like that training classifier is not in parallel. So that's why it's false. All right. Okay, so we're moving on to the Viola-Jones algorithm, and it is also implemented on the OpenCV. And like, and as this slide says, like we kind of like tend to use CNN or some like kind of like rich classifiers these days, but this method is still like kind of like popular and like easy implementation, powerful method to like do the detection of the face. And so here's some like problem of face detection. So the first one is, how can we define the features?
Hiding faces.
Kind of, yes. And so like we kind of want to search for eyes or noses, but like we don't exactly know how. Yeah.
Or like relative positioning of specific features, right? Because like if you see a face, you see something that is an eye,
Yeah.
you have to check if there's another eye somewhere nearby. And that's how you know, like, oh yeah, a face should have 2 eyes, or it means about something's an eye though. Well, we can break down to get more like granular feature spaces like an eye or a nose or something, right? An eye essentially. Instead of looking for like an eigen face, or searching individually for all these parts, we consider each specific parts to be like a flag for one specific area. But that probably also have to define search for the edges or the shapes.
Shapes. So I think like the algorithm kind of gets to that point eventually. So like I think we have some slide. Oh, so yeah. So like basically like those features are kind of found. So like the one in the like right. This one kind of like scan for you like eyes. And this one kind of scans for you nose. Kind of. Or is in going back a bit. So like we have like we have to like define the feature, and then we have to like select the like feature which kind of like make most of the sense, and then we need to do the classification of based on the like defined feature or selected feature. And the requirement for the feature is it must be like descriptive, and also it should be inexpensive to compute, because we don't want to use any feature that is like extremely expensive to calculate. And the last one is like compute is using only integer operation. This is kind of like connected to the like power consumption. If you can perform everything in the int space rather than the float or something, it's gonna be super inexpensive. That I think you can perform on the like camera or some like cheap processors. So going back to some like simple idea of like using a basis like the checkerboard. So the checkerboard is class agnostic, right? It's just a checkerboard. And if we can like represent the image based on the like combination of those like weighted combination of those checkerboard, it's gonna be a super inexpensive, right? And like but the like thing is since these checkerboards are like class agnostic, it may not be super descriptive. And we also learn BCT, right? CT, discrete cosine transform. Okay, and that one using a lot of like inner product, right? And that is kind of expensive. And we kind of want to have something in between those two. So like we want to kind of keep something like the checkerboard basis, but in a like localized manner, and kind of like able to pick up the like feature of the faces. And then that's where this slide comes in. So we are going to use like ones and negative ones. One is like white one and negative one is the gray one. And it kind of like keeps the like checkerboard like pattern. And we will use the like combination of like these four types of like checkerboard pattern to represent the like face descriptor. So for this horizontal one, we're looking for how much the difference in average intensity of the image in the black and white regions. So I think we usually have some contrast in this region. So we kind of want to detect that one. That's my understanding. And you can do the by the like dot product of the region of the face and the region covered by the checkerboard and the checkerboard itself, right? And we have like these like 4 base patterns, right? And they have the characteristic of lengths and widths, so it can like vary. And the type. And type is about the like arrangement of the bands. And this like for checkerboard is the like 4 bases used in the Viola and Jones algorithm. So um so it's not like I don't think it kind of like exactly corresponds to somewhere, but like we will like train based on like those bases to represent the feature as a weighted sum of those like elements. So so for scanning, what we want to do is to like store the like sum of all pixels from the left and above, like from left. So like we are kind of like summing from like left off to the right bottom, right? So we want to like store the sum of the old pixel from that location to the left or the above. And here's some like example. So that to compute the sum of the pixels within D region, we first uh we first can calculate the pixel sum of number 1 as area of A. And then we can calculate the pixel sum of 2 as area A plus area B. And then we can calculate the pixel sum of 3 as area A plus area C. And then we can calculate the pixel sum of 4 as A plus B plus C plus D. And then we can use that line to derive the area D is equals to pixel sum of 4 minus 2 minus 3 plus 1. Is it good? Okay. So so in order to compute the feature, the total like value of that black region corresponds to D plus A minus B minus C. So like D is that point, D plus A minus B minus C. And similarly, the total value of the white area can be calculated as F plus C minus D minus E. And then like final feature can be derived as the like combination of those two. So like white pixel corresponds to +1. So +1 plus -1 times this, the black area. Is this good? So like feature is the combination of those like white and black region, right? And this is the value for the white area. And the black area is -1. So you subtract the black region. Yeah. And we will have tons of like those features. It but I said tons, but like it's not infinite, right? So if we kind of like we can kind of like narrow down to some like reasonable numbers by limiting, I think limiting the size of image by 24 by 24 pixel, and that will like reduce the number of possible feature about that size. And then also we can like restrict the checkerboard size with minimum of 8 pixel wide and minimum of like 8 pixel height. And then we can also apply some other limits, and this kind of like reduces to total 50,000. So like not really all are like used, but we are kind of like going to greatly select the maximum of like number of weak feature, a weak classifier that we are going to use. So each possible checkerboard gives us like one feature, like we calculated in the previous slide. And total of like up to that number can be derived from the 24 by 24 image. But we are not using all of them. And now like every 24 by 24 image is represented by the set of that number, right? And this is the like set of feature we will use for classifying this is whether like face or not. And I'm kind of like repeating this, but like Viola Jones algorithm use ADA boost with stumps, and stumps is like something you can like easily calculate, and we will use the like feature that gives the best classification out of the training data, all of the training data. And the training data consists of like many example face and non-face image. And the classification rule is kind of like if the feature is like above some threshold, it detects as a face. And if the opposite, it's non-face. And we need to like determine this threshold to do the like good face classification. So what we are going to do to train the thing is we collect large samples of like image containing face and non-face and resize them to 24 by 24. And use this as a like training set. And oh yeah, sorry. So we have like face image for like face training set and non-face for the non-face training set. And combination of this is our like training set. It's okay. Okay. So for the testing, giving a new 24 by 24 image, we calculate the weighted combination of the feature with the train threshold. And as noted here, like only less than 10,000 features are typically used. So it's not like the super large number that we mentioned before. So it's like the subset. And problem here is typical features are much larger and they may contain many faces. And this way is not accurate enough. So what we want to do is to combine the classifier in the cascade way, but let me see. Sorry. So for the testing time, I think we want to classify each 24 by 24 rectangle as whether it is space or not. And for an n by m picture, we will perform that many classification, which is like n minus 24 by n minus 24. And we will merge the like 24 by 24 rectangles if they have some overlap. And we can use the same strategy as before to like do the like scaling thing. So we already have the classifier that uses the weak learners, and we uh, uh, what I wanted to say. Okay. So given the image, we can like scale down the picture by factor of alpha, and and I'll come back to this later. Oops. So we have poll 3. I think you might see the answer, but okay. So why 2, 3, 4 are wrong?
2 is wrong because OpenCV actively uses Viola Jones for their purposes, especially when it needs to be in real time.
Yes, that is true. Basically checkerboard is fine. And for like I think this is also checkerboard is fine. Okay, so coming back to the detection problem. So we have like two things. One is false rejection and the other one is the false detection. So rejection is when there's a face, but it cannot like detect as a face. And the false detection is when there's not a face, but it detects as a face. And we have this like standard classifier of, I think this is sigma and alpha, but we have like this standard classifier like this, but we can add some like bias term like y here to reduce the false rejection. So by adding some like number y, it will increase the chance of like being positive, right? And as a result, we can reduce the like false rejection. And we want to do this because we will combine like multiple classifiers. So whenever like that classifier classifies that region is definitely not the face, we can drop that region. And the second one will only focus on the remaining region and then do the same thing. And the like rest of the classifier do the like similar thing in a similar way. So only focusing on the like face-ish region and drop if they believe that is not the face. Is this good? So we can so ideally like false rejection will be 0% at the like right corner, and false detection want to be 0% at the left side. So we want to like move the boundary. So we want to move towards the like boundary to have like better performance. And as I said, when we increase the like y there, we reject less. We reject less. So like it will reduce the false rejections. But at the same time, it will like increase the face, like detected face. And it can be non-face, right? Because we just increase the y to make it answer more towards the face, right? And so the like idea is like, as I said, we combine the like multiple classifiers so that the classifier one first like determines whether that is face or not. And we drop the like non-face by classifier one and focus only on the like face region according to classifier one. And the classifier two performs the classification on that region and then drops the like non-face region and then pass to the classifier three and so on. And as this said here, if we set y high enough, so if we have like large bias, we will like never miss the face, but it will also produce junk face a lot. So like in order to like avoid the junk, we want to like combine in this way. Does this make sense?
Yeah.
Good, okay. So I think similar to this one, this figure shows like given the sub window, classifier one detects whether it is face or not. And if it detects as a face, or like it can be a like junk, but because we increase the y. But if it detects as a face, it passed to classifier two, and classifier two do the same thing, only on the like region where classifier one says true. And then classifier two does the classification and then pass to classifier three, and then so on. And after we have the like final classification result from the like last classifier, we do some post processing. So as I showed earlier, these are the like learn feature by the boosting algorithm. And it kind of like corresponds to like kind of like eye and like nose for like horizontal and like this vertical thing. So this cascade formulation syncs together with boosting. The reason why is because it's greedy. If you do the like strongest features first, you can make the early decision. If you have like simple features, you can make the fast classifier. This is harder to do with things like SVM or neural networks. Okay, so I think this will be the last one, I guess. So for the first one, do you think this is true or false? False. False. Are you sure?
Yeah, because if you increase the y, it should increase the threshold of acceptance, which. Oh, wait, no, it's the opposite. Never mind. It increases false detection while decreasing false detection because it should be more sensitive. So it's true.
Okay, that is correct. How about the second one? True. How about other people?
It's
You think it's true?
false because you must have like higher false rejection.
You think it's false? Because it has higher.
No, it has lower false, but should have like higher false rejection.
Higher false rejection rate. So false rejection is like, there's a face in the image, but the classifier like misses, right? So if you have higher false rejection rate, if you have higher false rejection rate, it means you are kind of like missing the face, right? So higher false detection is like you get like bunch of faces, including the junks.
Yes, but okay, yeah.
So higher false rejection rate means like the opposite, you get super less. So that part is correct. So the answer is true for this. I'm also kind of sometimes get confused with this false rejection and like false detection, but don't get confused. And yes. Oh, it's time? Okay. So I will just like show some like result of like using this classifier. So training is like training is done on like this kind of like image, and then you will get some like decent detection like this or that. And notice this is non-neural network, but it kind of works, right? And here's more detection examples. Oh yeah. And it kind of works, right? Okay. So about the implementation, it is like details are discussed in the paper. And the first like training time was like weeks at the moment, but I heard it is due to their implementation and it can be run within a day. And it's like, this is like super old time, but the resulting classifier can run in like 0.07 seconds in 2003 to do that detection. It's kind of like amazing, right? Impressive, right? Okay, so it's okay. So I think I'll stop here. Thank you for attending.